Okay, so last week I stopped here and I introduced many flows, such as the steady flow, unsteady flow, and like here showing the viscous flow and the inviscid flow. And some flow, we are talking about the nominal flow and the turbulent flow. Okay, so there are many flow conditions, and we already introduced in last week. So right now, I just would like to introduce some phenomena very important for when we discuss with the flow velocity field. Okay, as you can see, the example here, we have the particle. This is our object. And the line, what is the line in here? The line in here, the string line. So you can see the string line are far away from the object. The string line looks like the linear string line. But if the string line are closing to the object, the string line will become the curvature string line. And one of the very important string line, just horizontal, like the green line showing here. The point when the string line contact with the object, the point, the black point in here is we call that the stagnation point, 停滞点. And the point at here, the velocity will equal to 0. So the flow will stop in here. Okay? So the idea, you can see, we can highlight some flow attach flow along the object. The blue curvature I highlight in here, along this boundary, we call that is attached flow, because the flow attached with the object body. Okay, and some important phenomena, we call that the flow separations. That indicate the flow in here. Start from this point. After this point, the flow will separate. That means before that, the flow is attached with the body. But after this point, the flow will separate. So after the flow separates, you can see some AD flow on here. Okay? So we call that the flow, we call that the wake flow. The flow in here, we call that the wake flow. Okay? And the wake flow inside here, the regions in here, we call that will induce very large drag force. So in here, we will have the very large drag force. Okay? And in that region, we call that the low pressure zone. Okay, so that indicates if you see some region are wake flow, and under the wake flow environment, there is the lower pressure regions, and in that region we will have a large drag force. So what is the drag force? The drag force 就是拖曳力. So the drag force is the resistance force for the object, because the object would like to go into left. Okay, the object would like to go into left, but the flow direction is flow into the right. So the drag force will have the force directions as I show in the yellow colors. This is the yellow color in here. This is the drag force for the object particle. So in the following class, I will tell you the reason why we will observe the flow separations, because more dangerous terrible things from the flow separation is the wake flow. Okay, so that's the sentence showing here. We tell you, for the designers, we would like to reduce the flow separations. So when you do some designers, and like the automobiles and the airplanes, you should consider how can we reduce the flow separations. So that indicates the flow separation is a very dangerous phenomenon for our object. Okay, so this is, I just show one example. Maybe almost 70 years ago. You see, this is the bridge. We have one suspended bridge design, and the bridge is opened in July, but the broken on the November. Okay, broken on the November. That indicates the bridge only survived about the 4 months and destroyed. Okay, what the reason? So the sentence summarized in here, because the flow separations can lead to the structural failure, because the wake flow is unstable, and theoretically, the condition for the bridge broken is the vortex shedding frequency is equal to the structure nature frequency, and then you will see the structure will start to oscillate and finally collapse. Okay, so I can play the movie and you can see the phenomena for this case.
And the wind begins to speak with a roar that no man
it's not
can fail to
clearly
hear.
because the movie was taken about 70 years ago.
In a 40-mile-an-hour gale,
see
the
the
feather
bridge
span
certainly
weaves
is
like a
starting
ribbon in a swinging
to
twist
oscillate.
that you wouldn't believe possible
That's
unless
because
you
the
could see it as
flow
you do now.
separations and there are some wake flow. And the wake
There's an
flow
automobile caught on the
includes
heaving
the
roadway.
vortex
The
shedding on the
11,000-ton
wake
center
flow.
span twists
And the
and strains the
vortex
giant
shedding
cables that support it.
frequency
Cables of
is
6,300
equal
wire
to the
strands,
structure,
each 17 inches
the
thick.
bridge structure nature frequency. So you clearly can see start to crush. So it's very slowly because the frequency is very low. Okay, and then finally you can see
Back out of the danger zone, all stricken spectators are
in the
driven to
movie the
safety
people
as
don't
the bridge
worry
gyrates
because
like a nightmare
the
high above the river,
oscillate is
twisting,
very slowly.
turning, curling.
So the people just walk very slowly. Don't worry about the bridge broke.
The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself.
And then finally
Face
the
to face
bridge
with fate, his
just
destiny
broke
hanging in the
and
balance.
it collapsed.
Will he heed the last warning or perish with the doomed structure?
So as you can see, the finally
There it goes!
just destroyed totally. Okay, so the bridge only survived around the 4
Engineers
months
are divided as to the cause of the disaster. Some claim it was the
after
use of
the
solid
bridge
girders.
opened
Others
to
differ.
work.
But whatever the reason,
Okay,
Tacoma will
so,
rebuild.
the idea
this time a
is-
bridge that will not...
For the engineer designer, they don't care some phenomena, so they just build the bridge. Okay, but under some conditions, the bridge will have some structural oscillations. So this is a very good case. When we design the suspended bridge, we need to consider the flow separation problems, because the flow separation will have the vortex sheddings, and the vortex shedding is one of the oscillate force. The oscillate force have a certain frequency, And the oscillate frequency is equal to the structure natural frequency. The structure will start to oscillate again, repeatedly, and then finally will break. Okay, so maybe it is a very simple idea, but I just share to you, let you to understand. When we learn some knowledge in class, but this is very important phenomena for the engineering problems, like the flow operations. Okay, for the airplane, sometimes we will have some problem. As you can see, this is an airfoil, and if we have the incline angle too high, and the flow separation will occur at this point early. So if we incline the airfoils to the high angles, and the flow separation will happen more easy. Okay, so you can see that the flow, this is the final string line, and after that there are some vortex shadings and the AD flow. So in that region, we emphasize this is, we call that the wake flow regions. And the wake flow region have a large drag force. So that's why the airplane will going down and finally collapse. Okay, so you cannot have a very high angle for the airfoil for this phenomena. And this is another case. As you can see, there are some, this is a string line again. We have the string line. And the string line will pass through to the small hole in here. And this is V1, and the velocity cross over to the small hole. We call that the V2. The V1 velocity and the V2 velocity, how relationship between they. Okay, so I can tell you in that region, the velocity will become higher in that region. So the V2 velocity will larger than V1. In the following class, I will teach you the reason why. But right now, I just tell you the phenomena. So the V2 will larger than V1. And then the pressure in here, we call that the P1. And the pressure in here, we call that the P2. And I tell you the P2 will smaller than P1. Okay? So in case for the conditions in here, this is a lower pressure and a high speed velocity. The lower pressure and the high speed velocity. So this is a lower pressures. And what's the problem? As I tell you, the lower pressures, if you still remember, if we have the x-axis is the temperature. So this is a temperature and the degree, and the y-axis is the vapor pressure. So we have the y-axis is the vapor pressure. So this is the vapor pressure, and the unit is the kPa. And we have the one line. Maybe the line looks like the shape, like this curve. And I tell you the point after the curvature and the point on the bottom of the curvature. On the upper, we call that this is the liquid phase, and the bottom we call that the gas. So how different? If you have a lower pressure environment, so the pressure will going to down, right? So if you have a lower pressure environment in here, that indicates the point will move to down. So the phase will start from the liquid to move the gas. And if the air, the liquid flow in here to be the gas, and I tell you the gas will become in here we will have the gas bubble, and the gas bubble will broken some structure surface, will cause some problem, right? So in here the idea is the lower velocity will higher pressure, and the higher velocity will have a lower pressure. Okay, so and later I will tell you the reason why. But if you know the condition is the lower pressure condition in small hole, and then in here we will have a gas bubble, and the gas bubble will try to broken the structure surface. Okay, and this phenomena we call that the cavitation phenomena. And the cavitation, the Chinese we call that the 血池现象, the cavitation. Okay, so the photo I just show some example. This is the case, is the spillway, 溢洪道, the spillway. So in spillway, maybe we will have the higher, if the velocity is too high, and we will have the lower pressure condition, and the lower pressure condition will induce the cavitation phenomena, because the liquid becomes to the gas, and the gas to be the gas bubble to broken the structure surface. So it's very terrible. As you can see, this is the Euro surface, and this is in other case is the fan, and then you can see the surface of the fan also have some destroyed. Okay, so the gas is very power to destroy the structure surface. But the idea is, because in that condition we have the higher velocity, cause the lower pressure, and then we can observe the cavitation problem. So for the engineer and designer, we cannot have the higher pressure, right? A higher velocity. Because the flow velocity is too high, we will have a lower pressure conditions. And the lower pressure condition, we will have the cavitation problem. And the cavitation problem, we can see some structure will be destroyed. Okay? So that's the idea. So let's write down some sentence. The pressure cannot lower than vapor pressure. The pressure cannot lower than vapor pressure. If lower than vapor pressure, we will have the gas bubble. We will have a gas bubble. And this is, we call that the cavitation. Okay? So, based on this idea, in our laboratory experiment in the next semester, we will some experiment, we call that the flow observations. And in that case, you can see we will put the one object, and we control the flow velocity. And the different flow velocity, you can see a different straight line. And the area in here, we call that the lower pressure area, right? And in here, usually we call that the wake flow. So in that laboratory experiment, we can observe if we can control a different velocity, and to see the straight line change when you have a different velocity. So the most important for this laboratory experiments, we would like to observe the nominal flow and the turbulent flow. So the two ideas, we know that the the nominal. This is nominal flow, and this is the turbulent flow. And as you remember, we have the radial numbers is equal to the rho u d divided the mu. And so in this experiment, we would like to control the different flow velocity to have the different Reynolds number. And we know that we can use the Reynolds number to distinguish the flow is turbulent flow or nominal flow. So you can observe how string line changes based on the different velocity. Okay, so this is some example. If you don't put any objects inside your flow velocity field, and you can only see the straight line, they are the string line, and they parallel each others. But if you put the different object with a different structure shape, and you can see the different string line result. Okay, maybe I stop here, and